This video is Lab 5 for Physics 2211, Section N on Felix Baumgartner's freefall. In this lab, I'll observe the motion of an object falling and compare this motion to Felix's motion in his fall. I will use the observed motion to aid in modeling Felix's motion in his fall and to predict when he broke the speed of sound. Newton's second law, which is the change in momentum over the change in time equals the net force, will be used to explain the forces of gravity and drag that will act on Felix and the object we observe as they fall. For drag, we will refer to turbulent drag, which is the density of the air times the drag coefficient times the cross-sectional area times velocity squared. But in the lab, to ease calculation, we will assume all in the equation is constant except the velocity, and this constant will be represented by the constant b. I will also use the update formulas for velocity and position to predict the motion of Felix in a computational model. In Tracker, I will analyze the motion of a falling basketball. To begin, I create a calibration stick of the basketball's diameter, which is 24 centimeters, set the origin of the axes at the ground, and then create a point mass to track the center of the basketball's position, from frame 116 to 145. With this point mass, I will record and plot the change in y position over time. In GlowScript, I created two computational models which follow the same code with few changes, where one represents Felix's fall and one represents the basketball's fall. For the code of Felix, we set the mass to 110, the ball's position to 0, 39,045 meters, 0, the change in time to 6 seconds, obviously the g constant to 9.8, the j hat vector to 0, 1, 0, and the proportionality constant for drag to 0.0078. We made the while loop last until 228 seconds. We had the weight force, which would equal to the ball's mass times g times j hat times the negative. The force of drag times b times the magnitude of the ball's velocity squared times j hat, and the net force being the weight force and the force of drag. The velocity will be updated by the original velocity plus the net force over the mass of the ball times the change in time. And the ball's position will be updated through the ball's position adding the ball's velocity times the change in time. Next, the only thing left was the arrow scale, which we set to 20. This set the first arrow to the ball's position and the second arrow at the ball's position, with the first arrow representing the weight force and the second arrow representing the drag force. Now, for the coding for the basketball, everything follows the same suit except for the mass, which will be 0.624, the original position, which is 4.260, and the change in time, which will be 1/30. Everything else, the g constant, the j hat, the forces, the net force, the update expressions, the arrow scale will all remain the same. After completing the computational models, I have graphed the observed position of the basketball versus the predicted position, where blue is observed and the red is predicted. Next, I have Felix's velocity over time, which will be used to determine when he broke the sound barrier. For the positions graph, we can see there's a discrepancy as time increases, which I will begin to explain in the conclusion. Additionally, I will use the Felix's velocity graph to help explain certain concepts in the conclusion as well. With the collected and compared data, what does it mean, or what does it tell us? For the basketball's observed versus predicted position, the values begin to deviate greater over time, which is because of the assumptions of drag we used in Felix's computational model with the constant b, because the value I chose for b was to fit Felix's approximated terminal velocity and the time or distance at which he broke the sound barrier, which won't be the same average constant for the basketball's fall, because in reality, Felix's fall experiences a different drag over time, since he falls from the stratosphere, which is extremely high up and has a different density in the air. With the model, we can predict the time and position at which he broke the sound barrier, which is around 55 seconds in the fall, and at about the height of 26,300 meters. Additionally, from the lab, I can analyze the terminal velocity that Felix experiences toward the end of his fall. The model shows Felix's max speed to be about 373 meters per second, which can be seen in the velocity graph as it flattens or levels out. And it isn't much faster than the sound barrier, because it is reached quickly after breaking the sound barrier. However, it does match his actual max speed experienced during his fall, which was 372.79 meters per second, which means the model does a good job of modeling Felix's fall. Thank you.